Hello everyone. Today we Team Victoria gonna present advanced surface construction techniques. So this is my team, myself Shivendra, and my team is Jesse, Mark, and Nisak. First of all, we're gonna see technical details. So in this presentation, we will cover advanced surface construction techniques. They are sunk surface, skin surface, subsurface, Jordan surface, and Kunz surface. The idea is to take one or two curves or set of curves and to create a new surface which interpolates these curves. That is, the given curves are isoparametric curves in the noob surface. This is fundamentally different from the interpolation to discrete point and derivative data represented either by mathematical proof or by software implementation. We'll also discuss design example and GM lab demonstration after construction. So first is sunk surface. A sunk surface is the generalization of a surface of revolution. It is defined by a profile curve and a trajectory curve. In the construction of a surface of revolution, the profile curve performs a complete rotation about the axis of revolution, but the rotation does not have to be 360-degree and it is controlled by a trajectory curve. So here we can see this sunk surface figure. So here you can see the profile curve and trajectory curve in the figure 1. Profile curve is denoted as E0 to P5 in X and Z plane, and trajectory curve is denoted as T0 to T10 in X and Y plane. So if we rotate the profile curve along the x-axis in 360-degree, we will get the surface, but we are not going to rotate it in 360-degree. But instead of rotating, the path of the rotation is defined as trajectory curve. So these are the equations for the profile curve and trajectory curve. Profile curve is denoted as P of U and trajectory curve is as T of V. Denoting the non-zero coordinates function of P of U and T of V is by Px of U, Pz of U, Tx of V and Ty of V. The sunk surface is defined by S of U, V. This is an equation for sunk surface. So the curve S of U, V is obtained by swinging P of U about the z-axis and simultaneously scaling it according to T of V. Alpha is an arbitrary scaling factor. So here we can see the point, we have the points P0 to P5. We need to rotate them along the z-axis, but that should happen along the path of the trajectory curve. So if we scale the x and y coordinates of the P points, we rotate it along the z-axis and scale it in such a way it can travel in the path of the trajectory curve. So instead of scaling the x and y in such a way which follows the trajectory curve path, we are going to rotate the profile curve. We are going to rotate the profile curve exactly along the direction of the trajectory curve. So these are the equations uh, of if the u and v naught vector for S of u comma v. Those are defining the p of u and t of v. This is the equation for S of u comma v and I comma j. So this is the new control points that are defined when we rotate the profile curve along with the trajectory curve. So here this is an example for the sunk surface. So you can see the control points here. The figure 2a shows the control points of the sunk surface. So after the rotation, of the control points. Uh, you can see the figure 2b when the weight are applied and using the alpha is equal to 0.12, you can see the new sunk surface. These are the weights uh, of the sunk surfaces, and P and T subscripts represent the profile and trajectory curve. Both P of U and T of E can be either open or closed correspondingly. The z-axis is taken uh, to be the axis of revolution. Z-axis, sorry, this is the z-axis. If the profile curve sung about the z-axis and it's scaled by the trajectory curve in x and y direction, the generated surface looks like a profile curve in one direction, while in other direction it looks like a trajectory curve. So if you look from the top uh, of this, you can see the trajectory curve. If you look from the front, you can see the profile curve. So this is another example for sunk surface. The tube is shown below, where the profile curve and trajectory curve must be on the XZ plane and XY plane. In so many cases, this restriction does not apply. The profile curve is not in XZ plane because it is designed on the X and Z plane, and it is turned to the X direction. The trajectory curve is the line segment in the XY plane, but this is also called as Knoop's curve. You can see in this figure where the control points represent the profile curve and trajectory curve. Now my friend Jesse will explain the next type of surface curve.
Hello, I'm Jesse. I'm going to be talking about the skinned and swept surfaces. We diverge from the idea of swung surfaces and this idea of swinging curve around an axis. We set up a section of curves, a set of curves. Now we parameterize our XYZ axes in this U and V directions, where U is the XZ plane and V being the XY plane. And we create this set of curves in the U direction. We can mathematically define creating a surface based on this set of curves, based on B-splines with the equation here. And from here, interpolation occurs in the U and V directions. Now, I wanted to bring this up at the beginning. I feel like these four things here, parameterization, positioning, continuity, and weight, are very important concepts, not just in geometrical modeling, but also in a lot of math problems in science in general. So this idea of parameterization can refer to our U and V directions. Positioning refers to our set of curves being laid out. Continuity is our functions that we'll be using, continuous functions. Weight are parameters to scale, our knots. So we have this set of curves, and they all have different degrees, different common, different knot vectors. So we need to find a common knot vector in the U direction among this set of, we have 5 curves here. So this was called knot refinement. It was covered in a previous section. We do knot refinement, and we find a common vector and a common degree. And our common knot vector ends up being having 22 control points in the U direction. So it's quite a few points with any sort of larger surface. This number 22 could really increase exponentially and become quite unmanageable, I'm sure. So when we set up this 22 point vector, we essentially now have a grid of points in the u and v directions, and we can interpolate in the u and v directions and actually create a surface this way. This method can be very difficult to control exactly what the surface is going to look like. So to gain more control, we can construct a spine curve in the v direction, which we will interpolate across. So there is an equation here for the spine curve. Now our skinned surface is split into this spine curve and a set of cross-sectional curves. This now gives us a sort of skeleton or scaffolding for our surface in two directions, one in the u direction, one in the v direction. We have to consider what type of curves we're using in surface construction. The curves can be rational, non-rational, planar, non-planar. But depending on what kind of curves we're using, you're going to have to use a different method for surface construction. Non-rational curves, interpolations can be carried out in 3 dimensions, whereas the rational curves will need a 4-dimensional homogeneous space. We can calculate derivatives along the spine curve, which end up being perpendicular to the u curves, parallel to the v curves. These derivatives can help us in our surface construction process. This is an example here of using the derivatives, which I call vector v here, and you can show there's some you can see there's some calculations. So the derivatives provide constraints for calculating our surface, thereby gaining a little more control over what the surface is going to look like. So here we can see 2 surfaces, one on the left with derivatives, one on the right without derivatives. The actual bottom portion, it's a little tough to see the difference. On the top we can definitely see the difference in the control points, the way that they were being interpolated. We could change our spine parameters. This picture demonstrating how the distance that our section curves are being spaced out. Right here on the left, the distance is less. So there are issues with skin surfaces that can result in this switching back between 3 dimensions and 4 dimensions, and what kind of curves we are using to construct these surfaces. And we can utilize a smoothing function to scale our curve set in 4 dimensions. I didn't really get to the details about the smoothing function here, as this is I thought this was a more advanced topic. Here are some examples of skin surfaces. The picture on the left, as we can see, is kind of becoming more controlled as we go down, from the top down. At the top, it's kind of wild. It kind of gains more control going down, smoothing it out. The picture on the right really is a good example of showing this set of curves that we're using on the spine. As you can see, the spine is right down the middle. So again, we want to come back to these 4 variables. We have parameterization, positioning, continuity, referring to the functions that we are using for curves. Weights are referring to scaling our curves. Positioning being where our curves and our spine curve are actually placed. Can make a big difference. All these things can make a big difference on the surface that's generated. These things can also make a big difference in other areas of science as well. These things kind of pop up, and these are kind of things to watch for, and other problems also. So now we move on to swept surfaces, and we can give a general form of the equation for a swept surface, such as given here. So we maintain our u and v parameters and directions. We introduce this trajectory curve and also the scaling and rotation concept. Now, we could set up the problem as given here and we can actually solve this analytically and construct a surface this way. This is shown in the picture. However, the previous method is limited in that the rotation would actually have to be the identity matrix. When this is not the identity matrix, we need to formulate the problem differently. It no longer is an analytical solution with an equation that we can solve. It's a algorithmic process, numerical method to solve this, construct this swept surface now. So we use a global coordinate system and introduce a local orthonormal coordinate system with OX, Y, Z vectors, which moves along a trajectory curve now. Local orthonormal coordinate system, our XYZ coordinate system, is orthogonal. Normal referring to these normalizations that are occurring in our X, Y, and Z coordinates. Now we define our surface, our swept surface now differently, this equation, where we introduce this trajectory curve, this transformation matrix, and this diagonal matrix. This is representing these rotations. So like I said, now we need numerical methods to solve this equation, and we construct algorithms that, well, they're already constructed algorithms that are shown in the book. So we can combine skinning when constructing a swept surface using this trajectory curve interpolation, and the trajectory being the v direction. The algorithm, there are two algorithms given in the book. Algorithm 2 does not use trajectory interpolation, as shown on the top. The first algorithm uses trajectory interpolation and is shown on the bottom. I won't really go into the details of the algorithms here, besides the trajectories. And we can talk about twisting our trajectories. Again, these are the algorithms. Interpolation of the surface with trajectory and no trajectory when twisting. You see the trajectory definitely follows a path. When twisting and rotating surfaces with trajectories, they can exhibit this offsetting phenomenon where there are oscillations, self-intersections, interference from the points themselves that are generating the surface. So this is another issue in control in building surfaces. To deal with this, we turn to this B vector that I didn't really talk about, which is an orientation function for calculating coordinates, as we can see. Now we are calculating our Z coordinate based on this B vector. We can use a Frenet frame to calculate B, so our B vector, assuming our trajectory is twice differentiable. And we also end up with this end term when doing this. And the Frenet frame introduces another local coordinate system that moves along the trajectory curve. So kind of interpolating locally along our trajectory curve for this Frenet frame. All other issues that I've gone through, going through these surface techniques, we find one technique that works, but then we run into an issue with it. A-frame has issues at inflection points, interpolation, shrinking, here in the picture down to almost seemingly a single point there. Maybe it is, I can't quite tell from the picture. There are definitely ways to deal with this inflection point, but I'm going to kind of leave it here on these subsurfaces. Now again, in subsurfaces, we come back to these four concepts, these four variables. You can say parameterization, positioning, continuity, and weight, which themselves give you parameters. And we need to consider all of these things as we construct our surfaces.
Hi, my name's Mark, and I'll be talking about Gordon surfaces. So the main idea between Gordon surfaces is that we want to take two non-rational B-spline curves, and we want to be able to combine these into a new NURB surface. And while we can theoretically have this happen with natural curves in the homogeneous space, it's generally impractical to do this, and the 3D results end up being unpredictable. So if we do end up needing to actually work with rational curves, what we can do instead is we can use approximation methods to take our rational curves and make them into non-rational curves with some error bounding, within some error. So to take our curves, the main thing that we have to do is we have to make sure that our two sets of curves satisfy these compatibility conditions. The first condition is that CKU is defined on a common knot vector and CLV is defined on a common knot vector. What this means when both of our directions are defined on the common knot vector is that our curves are compatible in the B-spline sense, which is very important later. And then our next condition that we need to satisfy is that the U and the V condition parameters are bounded by 0 and 1, such that our QLK points are the same as our CKUL points and our CLVK points. And what I mean by that is that if we look here at our diagram, Q31 is the same as C1U3 and C3V1. And these are the exact same points. So our points in the V direction and our points in the U direction need to match up. And then when we're actually blending these surfaces, we have another condition that we have to satisfy, and that's this this equation 10.31. So because we only have this one satisfactory condition, we actually have a whole bunch of different blending functions that we can use: Lagrange polynomials, step functions, cubic splines. Gordon himself experimented with all these different types of functions, and the ones that you choose is really dependent on how you want the blending function to work. And because of this very simple condition here, we end up with this with 10.32 as our equation that actually describes what a Gordon surface is. And what this means, L1 and L2 and T, I will get into a little bit later. But and then 10.33 also arises from this very simple condition. And because we are compatible in the B-spline sense, we get these nice equations that we just need to add and subtract, and we get our new surface. Pij is gotten by the points, the control points are gotten by just adding and subtracting the our resulting control points for our various surfaces. So talking about a little bit more about the 10.32 equation, L1 and L2 are actually skin surfaces, and T is an interpolation of the QLK points, or it's also called a tensor product surface. And the way that we choose our parameters and knots for these surfaces is determined by the UL and VK points and the knot vectors for our curves. And to give it kind of an example of that, we'll look at CKU described by n equals 5 and p equals 3, and the knot vector you see, and CLV m equals 4, q equals 2, VC for our knot vectors. And the first thing that we're going to do is we're going to do unidirectional lofting or skinning in the to the L1 surface, and these are our resulting knot vectors. and that will give this control polynomial. So these control polynomials, like normal, you have to do knot refinement, and we knot refine on the u direction here, and that gives this surface, this lofted surface. So continuing, so we also do this to in the v directional lofting in the L2 surface, resulting in these knot vectors. And you can see here that our control polynomial is different and our surface is slightly different. This time we do the lofting in the v direction. And then we continue on, and we, instead of doing the lofting in the for the tensor product, we do interpolation to compute the knot vectors. So these are the resulting knot vectors here. And there's a slight difference between the VT and the VL2 knot vectors. And this is because the skinning uses control points, while interpolation uses intersection points of the curve network to define where the knot vectors are going to be next. But one problem that arises from this is that the knots can end up very close together, which is unnecessary and undesirable. And to fix that, one way that we can do that in our algorithm is to pass all of our previous knot vectors that we've computed to our next step, and replace all the new knots with existing ones where the difference is sufficiently small. And this is the control vector, the control polygon for the tensor surface, with again a slightly different surface. This is the overall algorithm that we have to do. And it's important to note that we actually have to take in the degrees of our different surfaces. So in our previous example, it wasn't shown, but the L1, L2, and T surfaces can all have different degrees, and what we do in that particular case is we actually elevate the other two surfaces to contain the same degree as the one that has the highest. So, for example, if L1 has the highest degree, then we would elevate the degree of L2 and T to be the same as L1. And then after we do that elevation, we would merge them to get our overall U and V, and then make our surface. And this is what the control polygon for the surface, for our Gordon surface, looks like. Now, so our control polygon, like I said before, because we are compatible in the B-spline sense, is just a simple addition and subtraction. There's no complicated mathematical operations that we have to do to combine these. And this is our final surface here. Thank you.
Hello everyone. Today we are talking about cone surfaces. A cone surface is a type of manifold parameterization that is used in computer graphics, which helps us to smoothly join other surfaces together, and in FEA, that is used in computational mechanics applications and boundary element method, it is used to mash the problem's domains into elements. The cone surfaces were developed or created in 1967 by Stephen Anson Coons, and they were generated by interpolation of four-edge curves that are the boundaries of the cone surfaces. The four-edge curve used for interpolation are also the boundaries of the cone surfaces. And binary interpolation is used for cone surfaces, which is done by performing linear interpolation between two different pair of corners, which are blended together later. And if you want to calculate or if you want to find a bilinearly blended cones patch, the equation below is used. That is S of uv equals to R1 of uv and R2 plus R2 of uv minus T of uv. And the T here is the tensor product surface. As I showed the equation to find the bilinearly blended cones, in the equation, the R1 and R2 are the ruled surfaces which lies between CK is equal to 0 of u and CK is equal to 1 of u, and CL is equal to 0 of V and CL is equal to 1 of V respectively, and the T is the bilinear tensor product surface. And below there is an example of the cone surface, how the cone surface would look like, and you can see the C0 and C1 I talked about. As I said in the first slide, a cone surface is generated using the interpolation of the four edge curves, or also known as the boundaries of the cone's patch. And in the figure above, we can see the closed boundaries of the cone's patch, that is A figure. And after the whole thing, the 2D representation of the cone's patch would look like that, the figure 2B. And to do the interpolation, first we need to do the interpolation between the top two corners and then the bottom two corners. And after creating two separate surfaces, we blend them together to get our resulting cone's surface. Now, how is the cone surface constructed? So, to create the cone surface, we need to do the interpolation between the boundary curves and the blending functions. The first figure shows, the figure below shows the binary blended cone surfaces, but the first figure is the ruled surface in the U direction, and the second figure is the ruled surface in the V direction. And I talked about it previously, that what a ruled surface is. To create a generalized cone surface, we need four rectangular surfaces as the input. But if you want to create the classical cone surface, we need four curves as the input. And all of them needs to satisfy one condition. That is, these patches, that all the curves should be in the same parameter domain where one boundary curve of each forms a side of the curvilinear rectangular, and the shape of the resulting surface can be changed if we change the shape of the constituent parts. Now let's talk about the bilinear surfaces. Here on the left side is a generalized bilinear blended cone surface. To explain that, let's assume we have four different points A, B, C and D, and along with that we also have four input curves P1, Q1, P2 and Q2. The 4 points A, B, C, D are at A is at P of 0, 0, B is at P of 1, 0, C is at P of 1, 1 and D is at P of 0, 1. And the curves that are P1, P2, Q1 and Q2 are between 2 points. Like the curve P1 is between point A and B, the curve P2 is between point C and D, while the curve Q1 and Q2 are between points A and D and point B and C respectively. And the final curve would be the P of UV in the center, that will represent our cone's surface, carried by these four above mentioned curves. Since it is bilinear, we need to perform linear interpolation on 4 points and 2 curves. So we can use points A, B, C, D with the 2 curves. Either they are P1 and P2 or Q1 and Q2. So let's assume the surface 1, That is, in surface 1, we do interpolation between points A, B, C, and D, and along with that, we use the curves Q1 and Q2. So the equation to form the surface 1 is given below, represented by R1, and since we already used the curves Q1 and Q2, for surface 2, we will use the curves P1 and P2 with the points A, B, C, and D, and it would be represented by R2 and the equation given below. And using these two equations, we can calculate the two surfaces, and I already mentioned it before, but to find the bilinear cone surface, the equation is given below, where we already calculate the R1 and R2 using the equations given above. And the picture on the right is the generalized cones patch that we will use to understand the equations. And since we already found the surface R1 and R2, the extra surface T is blended on ABCD, but that surface is linear in both U direction and V direction, and it can be calculated using the equation below. And after the whole equation is calculated of the bilinear blended cone surface, the figure below demonstrates how our final cone surface would look like. Now let's talk about advantages, disadvantages, properties, and the applications. So the advantage of the cone surface is that it requires very less effort. It doesn't require any complex steps for generation of the surface, but the only disadvantage that it have is that it does not allow us any precise control over the shape of the surface. And the properties are that the smoothness of the surface is equivalent to the minimum smoothness of the boundary curves. So the smoothness of the surface depends on the boundary curve, smoothness of the boundary curves, and it does not provide us the higher continuity across the boundaries. And it interpolates the arbitrary boundaries as well. And that it has various applications, such as it is used for plain artist or security printing, or it is also used to fill the holes in various patchworks, and it also has other special pattern design applications. Now a lot of people would downplay the cone surfaces, or would say that it is only used for some um, less important works or plain artists, as I have mentioned, but it is also used for various important printing. Now, bicubic blended cones surfaces. When two bilinearly blended cones patch share a common boundary curve, they only represent C⁻0 continuity across the boundaries, which means that combined surface will have a overlapping over the common boundary. We can remove this problem using the bicubically blended surfaces. These bicubically blended surfaces will smoothen the areas where the bilinearly blended cones patch have a common boundary curve, and eventually they will remove the creases that were formed. And because of this error, the bicubically blended cones patches were introduced. The four boundary curves need to satisfy these two equations, the equations of Ck and Ck of u and Cl of v. And for the four boundary derivative fields, these two conditions of dk of u and dl of v are important, as I mentioned here. When we want to create a surface with Ck of u and Cl of v as its boundary curves and dk of u and dl of v as its partial derivative fields around the boundaries, then the Ck of u and the dk of u along with the Cl of v and dl of v needs to be compatible with the B-spline sense. These curves and the partial derivatives also need to satisfy these twist vectors denoted by T of Kf. And the equation to find these four twist vectors are given below. The figure below shows us the comparable boundary curves along with the cross-boundary tangent vector functions and the twist vectors. So the boundaries are the boundary curves, and the pointed arrow that you see are the partial derivatives, and if you look at the tangents you will find the twist vectors. That you can also see that t of 0 1, t of t1 0, t0 0, and t1 1 at the four edges. Now let's talk about the algorithm used for bicubically blended cones. Here Ck and Cl are the arrays for the curves, and dk and dl are the derivative fields. These four are inputs, and the remaining variables represents the output of the surface. After that, we need to calculate the values of S1, S2 and T using the equations, which I will show you in the next slide. And after that, after we get those values, we need to calculate the degrees of CK curves and DK derivatives, and also the degrees of CK curves and CL curves and DL derivatives denoted by PC, D and QC, D respectively. And after getting the degrees, we substitute them here in the new variables P and Q. Now we need to do the degree elevations only if it's necessary using S1, S2 and T in the newly found variables P and Q. And if we do the degree elevations, we need to find the knot vectors U and V for S1 and S2 respectively. So for S1 it's not vector U, and for S2 it's not vector V. Later on, we subtract the new variable P and 2 from the number of U knots to calculate the knot refined N. And similarly for knot refined M, subtract Q and 2 from the number of V knots. And the last step will be to calculate the control points of our resulting bicubically cones patch. And to do that, use the equation below and plot our surface in the three-dimensional surface. I would show the equations in the next slides. As in the algorithm I mentioned, to calculate the S1, we can use the surfaces here, and to calculate S2, the equations that are needed are here at the bottom. And the two interior rows are derived using the Bezier derivative formula. And in the next slide, I will show you the equations for the T and the final curve. Here, to calculate the T of UV, as I showed in the algorithm, the equation to find the T of UV is mentioned below, and the T is the tensor product surface, which will have 16 control points. And to calculate the control points of our resulting bicubically cones patch, the following equation will be used. And the Pij is the final curve. As you can see in the figure A, it represents the control net for cubically blended surfaces in U direction, and the B is the surface in the U direction, resulting surface in the U direction. But here the Bezier is in the U and the B-spline is in the V direction respectively. And these are the cubically blended surface in V direction. The A figure is the control net and the B figure is the resulting surface. But here it's the B-spline in the U direction and the B's are in the V direction. You might have noted that for the cubically blended surface in the U direction, the B-spline is in the V direction and the bezier is in the U direction. But for the surface in the V direction, it's vice versa. The surface S1, S2 and D, if necessary, must be made using compatible knot refinements and the degree elevations. And after that, the final control points P of ij of the cone surface can be computed using the equations of Pij, which I already mentioned in the slides before. But here is the final equation that could be used to find the control points Pij. And that would be from my side. Now the designing part would be explained by my friend Shiv. Thank you.
So now I'm gonna explain about the design examples. So this is one example for the sunk surface. This is a half was. So in this, if you see the shaped curve, this is the profile curve, and this semicircle is the trajectory curve. If we sunk the profile curve along the trajectory curve, we will get this half was. So if we use the full circulation instead of half, then we will get the full base of the was. So this is another example for the sunk surface. Um, so for each surface curve, you can see the profile curve and trajectory curve, which is different. So this is the scaling factor. So if we change the scaling factor, we can able to see the change in the profile curve and trajectory curve. So once if we change this, we can able to see the curves uh, in different shapes. So this is this is an example for skinned surface. Um, the following four noob curves, which is the profile curves, the control points, which is generated in the skinned surface, are different from the control points which is in the profile curves. Actually, the control points of the generated skin surface are computed from the control points of the profile curves. Now is the GM lab. I will show the model for the geometric modeling. So this is a model which I designed for the GM lab. So this is an example model for the surface curve and skin smooth surface. So this is a reference which we used for this presentation. Now I will show you the model which I designed from the SolidWorks. So this is an example for the surface curve and smooth skin surface. You can see the curve where the profile curve and trajectory curve is represented. Thank you guys for giving us this opportunity. Yeah, and have a nice day.